So, Victor?
Okay. All right. Good afternoon, everyone. Welcome back to our seminar series. Today is my great pleasure to introduce our seminar speaker, Qiao-Jun Lin. Qiao-Jun Lin graduated from National Taiwan Normal University of Earth Sciences in 2017. She began graduate studies at the National Central University, where she got her master's degree in 2019 in atmospheric science, and she continued to pursue a PhD. Currently, she's in her 4th year of graduate school, and she's a business scholar in our department, working in our group with Professor Angel Adames. Her research is mainly focused on the Madden-Julian oscillation. She basically used climate models to understand the main process behind the Madden-Julian oscillation, which is in fact the title of the seminar today. A moisture mode theory-based assessment of the Madden-Julian oscillation in CMIP6 models. Okay, Qiao-Jun, yes sir.
Okay, thanks Victor. Hello everyone, I'm Qiao-Jun. Today I will share our work with you. About this work, the co-authors are Dr. Maida and Professor Adams. First, today we have to know why we want to do this research and why do we want to examine the moisture mode of CMIP6 models. Then I will tell you how did we do based on some criteria. And based on these criteria, we can know what model has a good simulation or bad simulation, so we can compare this model to know what are differences between the good and the poor models. And the fourth part is my conclusion. Firstly, I need to explain what is the MJO. The MJO is firstly described in 1971. It's one of interseasonal oscillation. The MJO can induce a large-scale circulation and the precipitation, convection, including the wet and the dry phases. In the wet phases, they will induce precipitation, moisture, convection anomaly. In the dry phases, there are the suppressed phase. The MJO can propagate eastward from the Indian Ocean to Western Pacific region. When it crosses daylight, the background mean surface temperature is cold in Eastern Pacific, so the MJO convection will disappear over here. MJO can influence different kind of weather system, including Asia rainfall, tropical cyclone, Australia rainfall, heat wave, and tornado hail frequency in South America. So many work have to want to know how we describe an MJO in theory. MJO can propagate, can oscillate. It looks like the wave. However, based on the space-time spectra, you can see here the Kelvin wave signal, equatorial Rossby wave signal, MJO signals over here. MJO can induce a large-scale circulation and the moisture anomaly. So actually, we can't use the dry shallow water equation to describe MJO. Many work have proposed different methods to describe MJO. One of them that is moisture wave mode or moisture mode. In the moisture mode, they emphasize that the precipitation anomaly are sensitive to the moisture anomaly. Moisture thermodynamics are important for the convection, and the moisture played a key role in evolution of convection and the wave. Previous study also proposed that the moisture mode criteria to examine that. First, the moisture anomaly has a high correlation with precipitation anomaly. Second, it needs to satisfy the weak temperature gradient balance. Third, the thermodynamic variation must be dominated by the moisture. I will explain this criteria detail later. But even though many work has discussed the MJO for the past decade, when we want to use a climate model to analyze the MJO or to understand what MJO change under global warming, they found that the climate models still have a lot of room to improve the angel simulation. This figure shows us semi-5 models. The shading is a precipitation anomaly, and here are the one observation precipitation and the other semi-5 models. We can see that, for example, their model show us the weak precipitation, and the signal can propagate eastward into the Western Pacific compared with the observation. So people, when they need to use the angel to do the work, they need to examine the model simulation firstly. But previous study focused on the mean state moisture and the sea surface temperature because they found that this background pattern has influenced intersignal scale, the angel. And some previous study also focused on the model simulation, parameterization, dynamics. They say the three factors are also important for the angel simulation in CMYC models. But free study has examined the angel-related thermodynamic theory in climate models. So in this study, we want to know whether the climate model can show us the motion mode of angel. And then we can compare the good and the poor model simulation to know what happened. We use the 25 CME6 models 20 years from historical run. And we also need observation and the real analysis data to compare with models. We focus on the boreal winter time because angel has a stronger activity during this period than boreal summertime. Because all data, their resolution are different, so we need to interpolate all data into a 2.5 by 2.5. We use a linear regression onto an angel components. First, we need to calculate the ORMA index. In the ORMA index, it only considers outgoing long wave radiation to do the EOF. So it can be used to examine the angel convection. We regret all variables onto the first principal component of EOF1 and that basic function approach, which means we use all data, model data, to act on the observed EOF to get their first principal component. Using this approach, in all data, the strongest angel convection appear at the 19 degree east at leg day 0. So it's easier and useful for us to compare the model and the model and the observation day by day. We focus on one poor region, especially this box, because based on the observed EOF, we can see that the angel convection has the largest variance over here. And according to the motion mode criteria, the motion mode of angel satisfied over in the ocean region. About the motion mode criteria, firstly, the motion anomaly has a high correlation with precipitation anomaly. We will use the scatter plot to calculate this result. You can see that in the observation, the both variables has a high correlation, lower than 0.9. We think the correlation should be larger than 0.9, which means the 80% data satisfy this criteria. The table shows us the result in the observation, ensemble mean of models, and the 25 CME6 models. You can, the green line is observation, the blue line is the mean of the models. You can see that many models, the correlation is lower than 0.9, which means some models can't satisfy this criteria. Second, the criteria need to satisfy the weak temperature gradient balance, which means the vertical dry static energy elevation is dominant in the heat source. They show you the observation result. the slope is very high, close to a 1. And compared with the models, our model can show us the slope is close to a 1, which means the least semi-6 models can satisfy the least criteria, the WTG criteria. Third criteria, the moisture dominates the evolution of moisture static energy, MSE. This figure shows you the result in observation, model with good result, model with a bad result. In the observation and the good model, the slope is larger than 0.9, satisfy this criteria. But in this model, the slope is lower, which means the contribution of dry static energy to the MSE is significant. So we can look at the all model result. Some models, the slope is lower than 0.85. So which means over here, some semi-6 models can satisfy this criteria. On the other hand, we also consider distribution of precipitation anomaly. This figure shows us a Homer diagram. In the observation, the precipitation anomaly over here and the model result. Homer diagram means the y-axis is a time, x-axis is a longitude. Over here, we need 2 indices. First one, we will calculate amplitude of precipitation anomaly. Second, the parent correlation between the model and the observation. We need the 2 indices because the amplitude can tell us to estimate the intensity of oscillation. The parent correlation will show the evolution. Compared with the observation, for example, 2 lines show us a very similar evolution, but you can see there the amplitude are different. So that's why we need the 2 indices. First table is the amplitude of precipitation anomaly. In the area 5 is close to the 0.6, but the model mean shows us a weak amplitude than observation. And the some model, the amplitude only the 0.2 is very weak precipitation. Then the parent correlation, you can see that the mean models is very lower than 0.8. So which means some models show a different evolution with the observation. Furthermore, we use the N mode to do the additional criteria. The N mode is used to diagnose the wave behavior controlled by the temperature anomaly or moisture anomaly. If N mode larger than 1, which means the temperature anomaly controls this mode, that is a gravity wave mode. If the N mode close to 1, they show us a mixed gravity moisture mode. If N mode less than 1, that is a moisture mode, which means the moisture anomaly is more important. This table shows us the shading is a shading means the wave should be the moisture mode, the blue shading, and the yellow shading shows us the wave should be the gravity wave mode. So here we can see that some wave should be the moisture mode, including the equatorial Rossby wave, tropical depression, and modern jet oscillation. The N mode is defined as this function, this expression. There, we need to estimate the phase speed of a gravity wave, MJO. Tau is a temporal scale of wave. Tau C is a convective moisture adjustment time scale. This table shows the result in the N mode, in the observation and the OR model result. In the observation, the N mode is close to 0.2, that is a moisture mode. And the moisture model shows us a moisture mode over here. But the 6 models has a gravity wave or mixed gravity moisture mode.
So can I ask a quick question? When you're calculating these indices and these correlations, are you calculating like a spatial average and then calculating the correlation through time, or how are you calculating these?
N mode? or criteria.
Any of these, like the,
We focus on the analysis region and each grid.
okay, so you have a separate point for each grid point through time, and then you look at the
And
correlation.
to show the scatter count.
Okay.
Thank you. So now we have many criteria. We need to do a quantitative analysis. For three motion mode criteria, we have know the all models satisfy these criteria WTG. And we also have a index related to the precipitation anomaly, and the additional criteria is a mode. So how did we do the quantitative analysis? Here, the error file result, we think that it's a true result in the observation. And we consider the standard deviation of the models and use 0.51, 1.52 standard deviation to set this interval. And when model result is located in certain interval, it will marked by the different color squares. If the model value is close to the observation, they will get the higher score. So this table shows us a result, and we order the model with a high total score to low total score, and there are observations. You can see that in the model with a high total score, that satisfy the four criteria and show us the N mode is controlled by the motion mode. In the model with a low total score, they only can satisfy the one or two criteria, and according to N mode, they show us a stronger motion mode and the mixing gravity motion mode. So based on this result, we can choose a 4-good model and a 4-poor model. We want to know what differences between a good and a poor model. But over here, these two models actually they're from the same research center, so we choose the poor one. First, we look at the mean state, especially the moisture static energy, MSE. Because many work use the interseasonal MSE budget to analyze the NGL. But some paper also propose that the mean state MSE will affect the interseasonal MSE budget, especially the horizontal gradient. This pattern shows us the observation, the MSE in observation, composite in good model, poor model, good model minus poor model. We focus on the horizontal gradient. First is the meridional gradient. In the 19° east and the 115° east, the observation and the good model show us the MSE. They have more MSE in the tropicals and the decrease with the higher latitude. So the meridional gradient is negative. Look at the 19° east. In the poor model, this figure shows the good model minus poor model. So in the 19° east, the poor model has more MSE than good model in the ocean region, especially on side of the tropical. And in the 115° east, the good model has more MSE in tropicals than poor model. So actually, the meridional gradient is stronger in the good model than poor model. For the
Sorry to keep interrupting. It also looks like in the era 5 for the west, the 90 east.
Yeah, actually the era 5, the pattern is similar with the good model.
In the
In the 19° east, there are more MSE in the tropicals than here.
Yeah.
So actually, I think that their distribution is similar to the good model. But in the poor model, you can see they are different over here.
Yes, over there certainly,
Yes.
but in the west.
Yeah, so I just emphasize the good model and the poor model. But I think the good model shows a similar pattern with the error, but the weaker than observation. Yeah. Okay. Yeah, also okay. We'll focus on the zonal direction. The good model has less MSE than poor model in Indian Ocean region, but more MSE in the Western Pacific region. So based on this slope, we know the zonal gradient is stronger in the good model than poor model. Then we focus these differences is dominated by the moisture. You can see the pattern show us the moisture and the dry stack energy. The pattern of the moisture is similar to the MAC. And the dry stack energy is close to homogeneous due to the WTG. So next we look at the low-level zonal wind. Because the background low-level zonal wind in the Western Pacific has a chance to stop and drain or propagate into the Western Pacific region. So this figure shows us the low-level zonal wind. We can see that there are the western wind band from Indian Ocean to Western Pacific region and maxima in the Indian Ocean. But in the model, they show us the western wind band stop at 116 degrees east, and their maximum wind is close to the Malay continent. Especially in the poor model, they show us a very stronger easterly wind in the Western Pacific region. So for the mean state, we use a parent correlation and a root square error in this result. We can see that the good model has a higher parent correlation, lower root square error than the poor model in most variables. So which means the good model can capture the more realistic mean state than poor model, especially a stronger horizontal gradient. Second part, we analyze the MAC budget, but I need to explain why we love to use the MAC budget. This figure, the shading shows us a precipitation anomaly. Control is the MAC, that is the intraseasonal scale. So you can see that the two variables, the pattern is very similar, has a high correlation, and sacrifice motion mode. So when we use the MAC tendency term, we can look at the MAC input before the extreme precipitation anomaly and then MAC output. So we can use the MAC budget to analyze the recharge-discharge processes of the MJO. In the MAC budget, there are MAC tendency term, 3 elevation term, zonal, meridional, vertical. We celebrate the horizontal gradient into a 2 elevation term because in the mean state we found that the good model has a stronger horizontal gradient in the meridional and the zonal. So we can check again over here. In the source term, there are the radiation and the surface fluxes. This figure shows us the shading is the precipitation, control is the MAC tendency term in the observation, good model, poor model. You can see that the model has a weak amplitude compared with observation, but in a good model, they show us a similar pattern with the observation. But in the poor model, the signal is much weaker than good model and observation. For the 3 elevation term, the control is the MAC tendency term. And I show you the zonal elevation term, meridional elevation term, vertical elevation term, in observation, good model, poor model. You can see that in the 3 elevation term, the vertical MAC elevation term is the largest elevation term. And the good model has a similar pattern to the observation, but the poor model shows us a much weaker signal than observation and the good model. For the source term, here are the radiation term, surface fluxes, and the residual term. Models don't show the good simulation of the surface fluxes in the Indian Ocean. According to a previous study, the surface fluxes is a big uncertainty in the model simulation. So we think that's the reason why they can show the realistic surface fluxes. Then look at the residual term, the residual amplified with the convection. We think there are some factors.
Why is the surface flux such a problem for these models? That doesn't seem like the hardest problem to solve.
Yeah, about the surface fluxes, maybe they need related to the wind speed and the relative humidity based on the close to the sea and the lower observation, there are differences. So I think the wind is the one apart
Okay.
because you can see that, and the second is the related humidity in the models.
Okay.
Yeah, so many model can show the good simulation in the surface fluxes.
That's interesting, yeah. Okay,
Does
thanks.
that coincide with you have a much stronger zonal weight in the observation than in the models, where you have a much larger surface flux at the same region? Because I remember the zonal weight is mainly over the land or over the maritime continents in models.
You mean the background?
Yeah.
Yeah, I think that's the other question.
Right. And then because you have a much stronger weight over the Indian Ocean, and maybe that's why you have more surface flux there as well.
Yeah, true. Maybe it's one factor. Thank you. So, a residual trend, you can see that amplified with the convection. Within there are two factors. First, we calculate MAC budget in the module output data. So maybe during these processes, there are numerical error. Second, the module output data, the resolution is very low. For example, the vertical resolution only provides us 6 layers. So in this situation, maybe it will underestimate the MAC contribution from the boundary layer. Okay, in the MAC budget, we can see that the good model can reproduce a realistic evolution of the MAC. In the poor model, they show us a weak convection and non-propagating. When we talk about non-propagating, we need to look at the Andrew structure. The Andrew is a couple Kelvin Raspberry wave structure. West of the convection, there are Raspberry wave. East of the convection, there are Kelvin wave. And we can use the low-level geopotential high anomaly to look at this structure. If you can't remember this structure, that's okay because this structure is similar to the scissors. So west of the convection, there are Raspberry wave gyres. East of the convection, there are the Kelvin low-level wind and the Kelvin wave structure. So the low-level easterly wind and westerly wind will converge over here to induce the Andrew deep convection. I will use the scissors to represent the Andrew structure and show you scissors anywhere later. This figure shows us shading is a precipitation, control is a low-level geopotential high in observation at day -5, day 0, day 5. Day 0 represents the Andrew strongest convection appeared in the Indian Ocean region. So at day -5, the Andrew developed in the Indian Ocean in front of land that are suppressive phase. And this structure, focus on the control, there are the Kelvin wave structure signal over here. And the total signals will propagate eastward close to the Manhattan continent. And you can see there are little Raspberry wave gyre west of the convection. At day 5, the convection is appeared in the Manhattan continent and very clear the Andrew structure over here. In the good model, you can see that the pattern is similar to the aerophile, but the shading that show us the weak precipitation than observation, and the weak Raspberry wave gyre at day 5. But whole structure can propagate eastward. In the poor model, first very clear, they show us the non-propagating, which means in the Western Pacific region, there are no precipitation anomaly, no convection over here. And the precipitation is very weaker than observation. At day 5, they only show us a weak Raspberry wave, but the Kelvin wave is mixing over here. We check the all good model. All good model can show the couple Kelvin Raspberry wave structure. But you can see that focus on the shading, the precipitation, the rainfall anomaly is weaker than observation. Something interesting in the poor model. This poor model shows us a standing wave, which means the convection appear, develop, dissipate in the same position. So that is a standing wave. And the Kelvin wave is missing in this pore model. Other pore model, this one can show us a clear wave structure. And here, they only has a weak rotary wave drive. We check again in the space-time spectra over precipitation. This figure shows the result in observation, and this figure is reference from a previous study. They used brine temperature. And you can see that the angel signal is over here like the envelope cover the wave number 1 to 4. This figure shows us a good model, and all good model can show us the angel signal like envelope with a wave number 1 to 3 or 1 to 4. But in this pore model, the angel signal is concentrated in the wave number 1. This model, the signal is concentrated in the wave number 4 to 5. I think that is not an angel signal. And here, the two band pore model can show us a very clear signal. So in this part, we can see that the good model can simulate the angel structure, couple Kelvin Rossby wave structure. But in the multiple model, the Kelvin wave are missing. How did we connect the angel propagation with the Kelvin wave? Because the Kelvin wave will induce a low-level easterly wind. It will trigger the shell convection in front of the angel. So based on the wind-induced surface heating exchange in this mechanism. So in many work have shown that if a thick convection can propagate eastward, the Kelvin wave is usually mixing over here. We can double check there based on the cross-section figure. The cross-section figure means the y-axis is a pressure or high, x-axis is a longitude. The shading show you the moisture anomaly, and there are zonal circulation. I also provide you a precipitation anomaly you can compare with the moisture and convection. In the observation, they show us the signal at day -5, day 0, and day 5. In the observation, in front of the angel deep convection, there are low-level easterly wind, and the shell convection, the moisture anomaly in the low troposphere. And the whole signals can propagate eastward. In the good model, the pattern is similar to the observation. But in the poor model, you can see that there are the weak low-level easterly wind and no shell convection developed in the Western Pacific region. So the signal propagates stop at 115 degrees east. It's very clear. Okay, there are my conclusion. In this work, we use criteria to extend the angel simulation in 25 76 models, especially the multi-mode criteria. We want to know whether the current model can show us a multi-mode of angel over in the ocean region. The answer is yes, but based on this criteria, we know no model can show the perfect result over here. Most model has a weak relationship between the moisture and the precipitation and the amplitude of precipitation. Based on this result, we compare the good model and the poor model. In a good model, they can capture the realistic mean state and the stronger horizontal gradient. And for the angel scale, they can reproduce a good evolution of MAC budget. But in the poor model, they show us the weak horizontal gradient, especially a stronger low-level easterly wind in the Western Pacific region. So in the angel scale, the poor model shows us a weak MAC budget and a non-propagating convection. On the other hand, we think the mixing Kelvin wave structure is one factor for non-propagating system in the poor model. So both results indicate that the multi-mode theory can be used to understand angel simulation over in the ocean. But actually, we can't only consider one index to say that this model has a good angel simulation or bad simulation because the angel characteristics can propagate its word in the correct phase B and can show us a good amplitude of representation anomaly. But we still think about why the poor model have a bad resolution. About the presentation is related to the parameterization of cloud, radiation, shell convection, deep convection in the model simulation. So actually, we want to do, but it's very not clear to celebrate these models just based on the one parameterization, because this parameterization will influence each other. There will interaction, so it's very hard to just based on the one parameterization to celebrate them. But we can think about why the Kelvin waves are mixing in the model simulation. Maybe it's the one factor, or what things influence the Kelvin wave disappear in the model simulation. So we think that's the one factor to influence the angel simulation in the climate models. I hope you enjoyed this presentation, and thank you for your listening.
Thank you, Qiao-Jun. I think it's time for a question.
I have a question. Very good talk. Thank you, Qiao-Jun. My question was going to be, if you had to make a guess, what is the, I wanted to ask you this first, without the guess. Is the Kelvin wave representation in the poor models poor all the time, or only when the MJO kind of starts to initiate?
You mean the different time scale?
At just different times in the model. So let's say you're in between, you're in phase 7 of the MJO, nothing's happening in the Indian Ocean. Is the Kelvin wave signal bad then too? Or does it just get bad when the convection starts to erupt in the spot where you expect the Kelvin wave will amplify it?
You mean the Kelvin wave in the model simulation?
Yes, in the model simulations, yeah. So is it always bad in the poor models?
Because we only focus on angel scale, so focus over here, we think the Kelvin wave in the intersignal scale or in my studies is poor in the format. It's bad in the format. But it's not represent for the model simulation whole time scale, whole region have a bad Kelvin wave, because you can see that in this poor model, they also show us a very stronger Kelvin wave in the time scale 3 to 6 in the tropical band. So it's also will influence other different weather systems, but also in the angel is bad.
Okay, that helps. I don't know how to read these diagrams. That was helpful. Thanks.
Yes, yes. Thank you.
Did you aggregated all these to a 2.5 kilometer resolution? Did you see anything in terms of resolution dependence between the good models and the poor models? Were the poor models coarser resolution?
Resolution?
Yeah.
Actually, I have one previous study focused on the radiation fluxes. We think the resolution will influence the radiation simulation, but a very little, because they think the resolution also will influence different time scale, different variables. So you can see that the high resolution model has just better result. You can say the main factor is the resolution. On the other hand, this model, run this climate model, the raw resolution is not very high than output data. Maybe I remember 10 kilometer. So I mean in the model when they run this kind of model, actually the grid is very high. But model output data, because they need to save this data, so they will output the data with a lower resolution.
Okay.
Yeah. So maybe it will influence, but some professor told me the influence maybe is weaker than the parameterization or other factors.
I have a question about the choice of aggregating observations over different types of MJO events. So what I mean is, sometimes the MJO propagates through the maritime continent and sometimes it doesn't. Do you think your results on what's considering good and poor models would be consistent across those that do propagate and those that do not propagate in observations if you were to separate that? Do you have any idea about how this translates? I'm just trying to relate that to whether or not it propagates or not.
In the model, we can divide the MJO event into the propagating and non-propagating.
Like if you were to subset your observations into events that did propagate across the maritime continent and those that did not, do you think that would have any influence on your conclusions about what are good and poor models in their interpretation, or do you think that not matters?
She said that you separate, for instance, if they propagate and propagate was successive and not successive.
You mean that if maybe we can celebrate the MJO event for good propagation or non-propagation to compare them?
Yeah, I was just wondering if your results is similar in both of those circumstances. I just don't know how to interpret that yet.
Yeah, we can do that, and if we also discuss this part, maybe we can choose the MJO event in the observation and the models, and to know what difference in the propagating and non-propagating MJO event. But what we just look at the total state, the characteristics, and yeah, it's a good topic. We can do that. But how did we celebrate the propagating or non-propagating event is the other question. Because based on some previous studies, because we show the composite result, right? So actually in the next 4 module, if we want to do that, I think mainly event is a non-propagating event.
Mm-hmm.
Yeah. So, but it's a further interesting topic because if we can choose all propagating event in the modules and observation, we only focus on the propagating MJO event.
Yeah.
Yeah.
Thank you.
Kind of following up on that, but in the composite mean for the observations, it is propagating, so
Yeah, that's
the
what I'm
majority of events
confused.
are propagating,
Yeah.
right?
Well, that's what I wasn't sure, because you were kind of comparing and saying the poor models weren't propagating, which implied that the observations suggest most are. But yeah, I wasn't quite sure like what really the distribution of what were and what weren't and how that gets muddied. Like, yeah, that was kind of confusing. Yeah.
I think it's very interesting to explore in detail these propagating and non-propagating MJO.
Yeah.
Vijay?
I had a question regarding the propagation of MJO. So if I remember correctly, like, there were some earlier papers which looked at like MSc budget, and I think they had like, you have horizontal advection of MSc from deep convection to the eastward part, and then that triggers some shallow convection which moistens it and then initiates deep convection. And so that is how the MJO propagates. And here, if I understand correctly, you're thinking that poor models, they don't have good Kelvin waves. Because of that, they don't have enough surface fluxes to show the eastward propagation. So like, I don't know, like if you have any thoughts, if you've thought about like the other horizontal advection component, is it the same between the good and poor models here?
I think you have that bars. Yeah, I think she did some analysis to analyze the propagation.
Wait. For previous studies, the Meridiano elevation turn is more important for the MJO's propagation. Wait.
The projections.
Oh yeah, here. We project the MAC budget onto the MAC tendency turn or MAC interested and we can see. Okay. The project onto the MAC tendency turn, it will show us which turn in the MAC budget is more important or have more propagation to the angel, more contribution for the angel propagation. If we act onto MAC is for angel maintenance. So the bar is the observed result, and the red line is the good model, green line is the poor model. So in the observation term, you can see that the good model has the stronger meridional elevation term. So, and according to previous studies, they say the meridional elevation term is more important for the angel's propagation. So maybe one factor.
Yeah, but that difference is not that large, I think. The Kelvin wave difference is more prominent between the good and poor.
But because this figure is focused on Indian Ocean, so I think if we want to focus on the propagation, we can move this box to the Western Pacific region. Because if you focus on the Western Pacific region, you can check the angel signal propagate or non-propagate to this region. So maybe we can focus over here to look at which term contribute to angel propagation or not.
Okay.
Yeah.
Okay. We have time for one more question. Okay, so that.
Given what you saw about the propagation and the wind speed over the maritime continent, between the good and the bad models, it would be interesting to look at the sea surface temperature distribution in the Pacific as well. And a lot of these models have a very strong cold tongue, and that would also likely impact the water circulation and the mean state over the Indian Ocean as well. So it would be interesting to see whether or not those wind variations are also associated with that extra strong cold tongue.
Okay, thank you.
Yeah.
We will do.
Okay. Good, time's over. Thank you so much. Thanks so much again.